So, for those who haven't been to one of these sessions before or have just come across us of late, my name's Jeff and I'm the founder and head of chemistry at Catalyst. So we run online chemistry tutoring and we also share organic content all over Instagram and TikTok, which you may have come across. So just to give a brief overview of what we do, we specialize in year 12 for you guys, HSC Chemistry tutoring, and we deliver some pretty good results. If you're still keen on joining us for the last term, our enrollments close at the end of this week, and our program for the exam intensive starts next week and runs for the next 8 weeks, all the way until the day of your HSC exam. So that involves, for the program itself, 4 exams, full-scale exams are timed, and we'll get that marked back to you before you review it the week after. And around that, you also get access to drop-in sessions where you can ask your questions one-to-one with our Band 6 tutors, as well as ask questions through text or email as well in between those sessions. So if you're interested, it's not too late to join. There's a lot of time left still to make a huge improvement because as you should know, the external is worth the same as everything you've done up until this point. So if there ever was a time to step on the accelerator and really take off over the next few weeks, it would be pretty much right now. And I know it's pretty soon after trials, but judging by the fact that you're here, it seems like you're taking it pretty seriously. I won't hold you any longer. We'll get started. Okay, cool. So module 8, we're going to run through the whole thing. If you have any questions throughout, feel free to unmute, put them in the chat, and I'll pause and answer the question. There will be a Kahoot at the very end, just on a mix of mod 5 to 8 questions. And there is a sizable prize for whoever does come out on top. Unfortunately, the prize is for non-Catalyst students only. So if you haven't joined us yet, you are able to claim that prize. Okay, let's get started. So mod 8, as you should know, is applying chemical ideas. It mixes together a bit of all the modules together, 5 to 7. And you're really looking at everything in a more analytical way, applying your understanding to actually do some analysis, which is exciting. As you would have seen over the course of the last term, you started off with analysis of inorganic substances. That was the first part. So you did inorganic. You then moved on to inquiry question 2, which was organic analysis. And then finally, you finished off with your compromise conditions and talking through all of those ideas with design of chemical synthesis. So we'll break down each of these topics. We'll try and move as quickly as we can. If I'm going too fast, tell me to slow down. And if you have questions, please stop me. Okay. Environmental monitoring. The first point of analysis of inorganic substances is basically, why do we do all this? The idea behind environmental monitoring is just that certain contaminants can get into waterways, soil, or the atmosphere, and they can be potentially dangerous. So we need to monitor using these specific analysis techniques to A, find out what is polluting, and B, how much is polluting. So that breaks our 2 types of inorganic analysis into qualitative and quantitative. Quickly in the chat, what are the qualitative analysis that we know of? What are some examples? Fire them off, there should be a fair few. Qualitative analysis. Qualitative inorganic analysis. As always, don't be shy. Test your understanding. Doesn't matter if you get it wrong. Bromine test, that is qualitative. It is organic though. Are there any inorganic qualitative tests? Inorganic ones. Nice, Anshita. So ion testing, flame test, perfect. Colorimetry is quantitative, so I'd be careful on that one. It is inorganic, I will say that. And okay, here they come. Precipitation, yes, good. Oh, I will put myself on do not disturb. That's probably important. Okay. Great. So we've got a few in the chat. Qualitative versus quantitative. The difference is qualitative is all about identifying something. So it's more just identifying, whereas qualitative involves quantifying. How much of something do you have? Have that distinction, and we'll go through each of the different methods now. You should know, take into your exam, a few common contamination sources. They can spring on you a question where they ask you to outline the consequences of X contamination, and you should be able to make some reasonable associations. So if they talk about, for example, eutrophication of waterways, and they tell you that these excess nitrates and phosphates have been let into a waterway, you should know, because this is one of the more popular case studies, that would have certain consequences such as these. It's neurotoxic. It can deplete the oxygen from the water, which kills aquatic life, and there's a few other consequences there. So I would say take at least one case study, whether it's eutrophication of waterways, heavy metal accumulation, or your disruption of pH from acid-base spills. So this one overlaps with your module 6. I'll take one of those three. In terms of your ion testing, you have cationic testing and anionic testing, and lots of these qualitative tests fall underneath this whole big category. So cationic testing, you're going to be talking about anything to do with positively charged ions: barium, calcium, magnesium, lead, silver, copper, iron 2, and iron 3. You should be able to differentiate all of these ions, and if you have a flow chart, this makes this whole process infinitely easier. Once you memorize a flowchart, you can never make a mistake in an ion analysis question. That is the bottom line. Getting to that point of having a flowchart memorized is a slog, I will admit. But if you have a flowchart, which I'll give you, you can use that, and you can almost certainly guarantee that every time you get a question about ion separation, ion identification, it is systematic and you will get it right. Okay. On the other side, you have anions, which are negatively charged, and it's all of these ions here: chloride, bromide, iodide, hydroxide, acetate, carbonate, sulfate, and phosphate. So those are the ions we're going to be separating. Return to that idea of qualitative versus quantitative. These are all the qualitative tests. What we learn flame test, precipitation. Complexation is one that a lot of people really struggle with, so we'll talk about that at a bit more length. And then in your organic qualitative analysis, you have your functional group tests. Technically, NMR, mass spec, IR, they're all qualitative too. Quantitative is everything: gravimetric analysis, precipitation, titration, colorimetry, UV-Vis, AAS. We'll talk about those as well, because a lot of people struggle on exactly how those work as well. Okay. Flame test, as we should know, is you put metal, usually in solution, you dip a non-reactive rod, like platinum rod, into it, place it into the flame, and you see a different color based on the metal. The reason you see that different color is because every single metal atom has shells around it, and an electron can jump up to a more excited shell or a higher energy shell when it gains energy from the flame. The flame provides energy, the electron takes up the energy, and it ends up at a higher energy level. Is this where you see the light? Yes or no? From the electron going up to a high energy level? No, 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 no. Good. So when do you see it? When do you see the flame color? When it returns, perfect. So when your electron falls back to ground state or a lower energy level, this is when you have the emission of that same packet or same amount of light. So you have a photon with same wavelength. And for every single interval for a metal, it is going to be a different wavelength. And that is why for different metals, which all have different intervals in the visible spectra, they will all have different colors. Hopefully that makes sense. The colors that you need to know, or what you do need to know, you need to know, one, the method of how you do this. So I've got two methods here if you do want to look over them, but you also need to know the colors of the common flames that you're going to see. The syllabus listed ones are in this table. You should know that barium is apple green, calcium is brick red, magnesium is no color, lead is gray, silver is no color, and a caveat with magnesium, it actually shows a bright white. So you can also note that. Sometimes you see that. Copper is blue-green. Iron 2 and iron 3 are green and gold or orange and brown. The other ones that don't appear in the syllabus but sometimes actually can get tested are lithium, sodium, and potassium. So they are crimson red, yellow, and lilac if you want to take those as well. Other caveats, you do not want to use a lead flame test because it is neurotoxic. So avoid recommending a lead flame test, but you do still need to know the color. So you wouldn't recommend it, but if they give you a lead flame test, you should know the color. Number two, iron 2 and iron 3 are actually quite similar in color, and literature really varies on this one. So don't separate iron 2 and 3 using a flame test. You should separate them using precipitation. The colors are much, much more different. Okay, flame tests. Any questions? All right, let's keep moving. So precipitation tests. You should know your solubility rules. If you don't, it's probably a good time to take them in. Solubility rules, you can either learn them manually or you can remember NAG, ZAG, PMS, Castro, Bear. I won't go over those in too much depth, but just a flag in the sand, you should have these memorized. If not, you always have your data sheet where you have these solubility constants. These are all the insoluble ionic compounds that you come across. The only ones you want to be careful of if you do use this method are lead chloride, calcium hydroxide, and barium hydroxide. You can see that those have a KSP, which is relatively large. So that means they are slightly soluble and in some cases can dissolve. But as we know, solubility is a whole spectrum. So some things are very soluble and some things are only a little bit soluble. There's nothing to define when it comes to what is fully soluble or not. It's just a spectrum. Okay. So when you're testing for precipitation, you're testing when you combine two ions together, an anion and a cation, is a precipitate forming. But based on whether it does or doesn't, you can say what options possibly could it be. The main things you should take away would be the main colors of certain precipitates, particularly the ones that are non-white. So the ones that are essential to know would be lead iodide and silver iodide. You should know that lead iodide is a very bright yellow and that silver iodide is a sort of paler yellow. It's more of a cream yellow almost. So you can still differentiate lead iodide and silver iodide. You should also take copper hydroxide being blue, iron 2 hydroxide being green, and iron 3 hydroxide being brown. Those are the musts. Everything else that is colored, you still want to note. So silver bromide, you'd want to note that silver hydroxide is brown. And there's a few with phosphate and carbonate, but we don't really test phosphate and carbonate too extensively in this way. So I would say know the ones I've highlighted in pink as a very minimum. And if in doubt, guess it's white. That would be my advice for the precipitation if you don't want to do the high band 6 level of memorize everything. Complexation. A complex can be defined as a metal ion, a metal cation in the middle. We call that the central metal cation. A complex is formed when you have what we call ligands arranging themselves around that central cation. So this, and this, these are all ligands. And ligands are simply molecules or ions that are attached to the central metal cation using what we call coordinate covalent bonds. So how is a coordinate covalent bond different to a covalent bond? Type in the chat or unmute if you know. How is a coordinate covalent different to a normal covalent bond? I think some schools might call it a dative bond as well, but I prefer coordinate covalent. Only the ligand donates electrons. Good. But then wouldn't that make it an ionic bond? So how's it different to an ionic bond then? I wouldn't say it's only one electron. How many electrons are shared between them and who is donating them? Ella says 2 electrons derived from the same atom. Perfect. So essentially, it is a ligand that has 2 electrons, such as this. You see that the ligand here is ammonia. It has 2 electrons forming a lone pair. And in forming a coordinate covalent bond, what happens is those 2 electrons are donated to the metal cation, in this case, silver. So they end up forming a coordinate covalent bond, which is formed from the 2 electrons being donated from the ligand. And they share those 2 electrons, the same as a covalent bond. There's 2 electrons being shared. The difference is that they originate from the ligand purely. And that forms what we refer to as a coordinate covalent bond. So ligands bond into a central metal cation by coordinate covalent bonds. That's why you can have like 6 of them around a cation. It's because all the electrons come from those ligands surrounding. The other things important to know about complexes would just to be that this process of coordinate covalent bond formation is actually what drives Lewis acid-base reactions. So a lot of schools don't touch on Lewis. I wouldn't worry about it too much, just for the sake of name dropping it. This is the same mechanism as Lewis acid-base, and we should be able to notate a complex. So for example, here, I'll define this a bit better. This is cobalt chloride, which is your case study from Mod 5. It's 4 chlorides around a central cobalt 2+. And hence, when you notate it, altogether in square brackets, it is a cobalt central metal cation surrounded by 4 chlorides, which each have a 1- charge. And the overall charge becomes -2 because it's +2 for the cobalt and it's 4 times -1 for the 4 chlorides, together giving you a -2 as the charge. I'd say they're the main things to know about complexes in terms of the background, and why we actually care about these complexation tests. It's because we can use them as confirmations after we do a precipitation, usually, to figure out what ions we have. For example, is it copper or silver or acetate ions? We can use it to differentiate those 3 for sure. So the ones that I would take as case studies, again, you should know the copper complexation reaction test, which is when you add, I'll do it at a bird's eye view. When you have copper in solution dissolved, you'll have a light blue solution. If you place a small amount of hydroxide or even a small amount of ammonia, what's going to happen is you're going to form copper hydroxide. And that is a light blue precipitate as well, copper hydroxide. So once you have that precipitate, the confirmation test comes after that. The confirmation is here, where you add an excess of ammonia to that solid, and what will happen is the solid redissolves, forming a deep blue solution, where the complex is copper with 4 ammonias around it, as well as 2 waters, and that becomes soluble and is deep blue, whereas the copper hydroxide, which was solid, is light blue and solid. So the confirmation test is that you are able to redissolve copper hydroxide solid into a deep blue ammonia like complex around copper. That's the idea. Okay. Any questions there? Because that's a bit confusing for most. Cool. If there are any questions, keep them coming. And I will move on to silver complexation and the acetate as well. These are similar, where in the production of silver chloride, solid, you can test it. You can test its presence by adding excess NH3. And if you add NH3 to silver chloride, you make the silver ammonia complex we saw before, and that ends up being aqueous as well. So you redissolve that solid into a soluble complex, and you see that the solid you had turns back to a colorless solution. And that is the silver complexation reaction test. You precipitate with chloride, and then you redissolve the silver chloride with excess ammonia. Finally, I think this is probably the most important one of the three, because it's very hard to identify acetate otherwise, is if you add iron chloride to acetate, you get a soluble complex iron acetate, iron with 3 acetates around it. That can be turned back into a colorless solution by adding HCl. How does that work? It's an equilibrium. Can someone try explain? You're adding HCl into this equilibrium system. Why does your solution turn back to clear? Acetic acid is formed. Acetic acid is formed. I mean, I would say a bit more direct than that. Equilibrium shifts to the right. Good. That's more what I was after. So if we look at this equilibrium at the bottom, I think this is the one that Anshita is referring to. If you add HCl, you are adding in chloride ions, which is going to in turn shift to the right, shifts to the right, which brings down chloride, brings down the iron acetate complex, and instead makes back your colorless substances. So you would see a decoloration from the addition of HCl to the iron acetate complex. And that is the conformation. Okay. Okay. In terms of flowcharts, there are many out there. I will just give you these as the ones that I used back in the day. This one's here for the cation testing. I'll give you a 5 seconds, take a screenshot if you want. It'll be all up in the recording anyway, but if you want to take them for now, you can go for it there. And then the anion testing, the main one I would follow is this. The conformations for anion testing are a bit more left of field. So I would say at a minimum, know how to separate everything from precipitation. And for the cations, you should be able to identify a conformation test for each of them. So whether that's flame testing or a precipitation test or whatever's listed here, you can follow those. But for anion testing, it's a much more complex because all of the conformations are a bit stranger. So I would say as a priority, precipitation tests to separate everything. Secondarily, learn conformation tests for cations. And if you want the higher range band 6, learn conformation tests for anion testing as well. But you'll get by just fine without the conformations if you're just going for a reasonable mark. Okay. Qualitative inorganic testing. There's a question here. There's an answer. We're not going to go through that. And we won't go through that question either. Okay. Gravimetric analysis. We should know gravimetric analysis is analysis of mass. So when you do gravimetric analysis, essentially what you're trying to figure out is based on a amount of mass that you produce, you should be able to find out the number of moles that you have and then therefore convert and find everything else. So it's mod 2 back from year 11, basically. More or less relatively straightforward. Are there any questions on gravimetric analysis? A question stem would look something like this. Okay. Precipitation titration, very similar to a normal titration with an important difference. What's the really important source of error in precipitation titration we cannot ignore? If we use an, that'll give it away. Yeah, so I would say the main source of error is what Ella's said in the chat there. I would say that it's the fact that your indicator for precipitation titration is not as effective as a pH indicator. So normally when we do a pH titration, the curve looks like this. And when we jump from a pH in one drop, we traverse the whole range and we see a massive color change in the one drop. And that means that our equivalence point is virtually equal to our end point. What's the difference between equivalence and endpoint? Super important concept. Difference between equivalence and endpoint. Equivalence versus endpoint. Okay, nice. We've got a few good answers in the chat. So to summarize, it's where you have equivalence point is where you have equal moles added of what you're reacting and what you're titrating with. And endpoint is actually when you see that change. Whether that's a color change or it's a color change, formation, or precipitate, you're observing an endpoint. The equivalence point is a mathematically defined point where you neutralize everything or you've completely reacted everything. The big point in a precipitation titration is that when you're forming, once you've finished forming one precipitate, the indicator you use is actually another substance that gets precipitated. So you'll have in solution, for example, in Moore's method, you have silver nitrate and an unknown concentration of chloride ions, 2 drops of potassium chromate, and that's your setup. So essentially what you're reacting is silver nitrate, aqueous plus Cl minus, and this is what is unknown, to form AgCl solid plus NO3 minus AQ. That's your precipitation in Moore's method. The moment you stop, or the moment you finish this reaction, as in you've precipitated all of the chloride, the way you see a color change is through an indicator which is slightly more soluble than the AgCl you were making. So that means that silver chromate will only start to form and show its color after the silver has precipitated all the chloride. So this is step 1, and then this is step 2. And in order to see a color change, you have to add a significant amount of silver in order to see the silver chromate. It's not as instant as a titration. So what that can mean is you might end up adding an extra mil or extra 2 mils even of your titrant before you see this silver chromate forming. And that creates what we refer to as titration error, where you have a higher endpoint when you stop your titration than your equivalence point. And the difference between equivalence point and endpoint, the difference between equivalence and endpoint is your titration error. They love to ask you on this and how you interpret titration error. Very, very common question. So for precipitation titration, if you're using an indicator, the way you bypass this is you will use a blank titration where you titrate the indicator on its own. And that allows you to figure out how much volume do you have to add to just get a color change from the indicator. And that will determine your titration error, which is the difference, once again, between equivalence and endpoint. So that would be precipitation titration. You can also bypass the titration error by, instead of doing a indicator-based precipitation titration, you can instead do a conductometric precipitation titration, where that equivalence point ends up just becoming a sharp corner on your conductivity scale. And as we know, as you're neutralizing your silver chloride, or you're reacting your chloride ions in solution, you're getting rid of chloride, your conductivity will drop. You reach an equivalence point where the corner changes. This is the point where you've run out of chloride to precipitate. And instead, on the way back up, you are now just adding in silver nitrate. And that will make Ag plus and NO3 minus freely, which, as we know, the more ions you put in solution, the more mobile charge carriers you have. And once again, the conductivity will reverse and actually start coming up from that point. And we don't have any titration error here. So two ways you can get around it. Both are entirely valid. Okay, quantitative analysis, big stuff to talk about here. We should know that the electromagnetic spectrum is the range of wavelengths all the way from like very short to very long. And the order of them is a range from radio waves all the way up to gamma rays. If you want to be very thorough, I'd memorize the order, but it's more of a physics thing. What you do need to know, I would say, is where the visible spectra lies, and it lies between wavelengths of about, give or take, 380 up to 750 nanometers. It varies, just have a rough idea of where it is. You can even consider it 400 to 700. And you should know the colors. So Roy G. Biv as the order, going from red, orange, yellow, green, blue, indigo, and violet. Revising the two types of spectra we see, apart from the continuous spectra, so this is continuous, which has the whole, all of the wavelengths and all the colors, that's our continuous spectra. There are two spectra that have only parts of the continuous spectra, emission spectra and absorption spectra. Emission spectra you get from exciting an element and having the element emit light when the electrons fall back down to ground state. This is what we see in flame tests. And it's why flame tests only show specific colors, because they might only show, say, a green beam and a yellow beam of light, and combined that might make something greeny yellow. The other form of spectra that is pretty important for us to know as well is absorption spectra. So this would be the case where you take visible light, you shine it through a sample, some of the light is absorbed, and you would get a reading like this. You would have bands missing. So what's actually happened here? What's happened is that your atom, which initially had 3 shells, it has had electrons excited up to energy level 2 and 3. That has then taken those wavelengths out of the spectra, which is correlating with these two bands that have gone black. It means that those wavelengths are now missing. And hence, you can detect how much of that wavelength is absorbed if you analyze those wavelengths specifically. And we use these absorption spectra for our quantitative analysis, which we'll talk on just now. Okay, so the big idea from all of this is understanding that electrons going from low energy to high energy levels take in energy. When they fall from high energy to low energy, they release that energy out and we can see that light. If that makes sense, then all of your remaining spectrum here will use that principle, basically. That idea of absorbing energy and re-emitting it. Colorimetry. Lots to talk about here, but I'll try to keep it simple. Basically, colorimetry is where you have a sample that is colored. Sample that is colored. In order to analyze that sample, we have to shine through the sample the wavelengths of light that it absorbs. So if a sample is blue, why have we chosen orange light? Why do we choose orange light to analyze a blue colored sample? Complementary, great. To analyze any solution, you have to use the complementary color because that is the wavelength it will absorb. The reason why you see this solution as blue is because it has absorbed its complementary color of orange. And if we're going to analyze how much there is, we want to select the wavelength that is complementary. So the idea is then, if you shine through this orange light, I'll actually use an orange pen, an orange light, This would be the intensity before the light passes through, I naught. And some of it will be absorbed by the solution, and you'll have an IT. I like to label it IT, just to make it very clear. The transmitted intensity. What will be higher, I naught or IT? Which intensity is higher? I naught versus IT. Good, I naught. Great. So I naught is greater than IT. And this idea that some of the light is removed, you can find out how much substance is in the solution based on how much light was removed. The more light you remove, the lower your transmitted intensity will be. And vice versa. The less substance that's in the solution, the lower the concentration, the less light will be absorbed of that wavelength. And the whole setup that comes before it is just preparing you to put that light in. Essentially, you just have a visible light source, you have an aperture or a slit, the condenser puts it through the filter in a narrow beam, and the filter selects your orange wavelength. So that's colorimetry. So why do we care? Few equations that are really important to us. This one here, if you get it in your exam, it's a free 4 marks. A equals ECL, or epsilon times concentration times length, which is also equal to the log of I naught on I, which can also be seen as log 1 on transmittance. And transmittance is equal to IT on I naught and will always be less than 1, like less than 100%. You should know how to use this equation. Epsilon is the molar absorptivity constant. Concentration is concentration in mole per liter. And lastly, length is the length of the cuvette that light passes through. So if your cuvette is 1 centimeter long, your length of light passing through the sample is exactly 1 centimeter. And oftentimes that's the length of your cuvette that you use. The unit is actually 1 centimeter, so you don't have to convert it. That's pretty much all I have to say there. Once you understand how it works, the way that you figure out concentration or you figure out absorbance is either by using the Beer-Lambert law. 1, Beer-Lambert. If you have epsilon, that allows you to convert absorbance into concentration. But if you don't have epsilon, you have to construct a calibration curve. And you construct a calibration curve by using known concentrations, so standard solutions. You test their absorbances and construct a line. So you test their absorbances, which can be found by log 10 I naught on IT, and plot your curve as shown here. And then from that point onwards, you can take an unknown concentration, for example, you take an unknown concentration and say it absorbs 0.6. You can then dot across in your graph and find your unknown concentration by interpolating on the graph. And in this case, it looks like it's about 0.000 for, let's say, hard to say, 47, let's say, molar. So there are your 2 ways. You can use either Beer-Lambert or construct a calibration curve and find it through that method. Again, some questions, we won't go through them. Any questions on colorimetry? Okay. UV-Vis. UV-Vis is relatively similar to colorimetry in its method with some key differences. Key difference is it goes into the ultraviolet range. It also encompasses the visible range though, so it kind of just is a bit wider in what you can test. So that means in the setup, you instead have a deuterium lamp. The deuterium lamp will shine in the UV range, and the visible light source we often use is a tungsten lamp, and you can use that for your colorimetry as well, a tungsten lamp. Now, the way we select the wavelength for UV-Vis is the key difference. We don't observe a color and select the complementary color. That's what we did for colorimetry. For UV-Vis, the way we find the wavelength we want is by setting up this whole system where we have a filter, a monochromator, and we split a beam into two separate beams of identical intensity and shine it through a reference sample as well as a sample of our solution. I naught is taken from the intensity that passes through a reference sample, and IT is taken from the intensity that passes through the actual sample. And this allows you to compare the absorbance of the reference versus the sample. And what you're going to do is you're going to sweep across the whole UV-Vis spectrum from about 200 nanometers up to the 750 nanometers. And you'll find that you get a curve of absorbance, and you're finding the absorbance through A equals epsilon times length times concentration. We're presuming that you have access to epsilon here in order to make this curve. Actually, no, you don't. Sorry. It's not this equation. It would be A equals log 10 IT on I naught. I naught and IT. Allows you to plot this curve for each individual wavelength going through the whole spectra. And so you find that some wavelengths are absorbed more than others. So if you wanted to analyze this specific sample, we want to take as high of a wavelength as possible, as high of an absorbance as possible, because that is the specific wavelength. So this one here, whatever it is, that is a specific wavelength which absorbs the most light and will allow for the most accurate analysis. So in this case, it looks like about, again, 500 just at a glance. Actually, probably more like 600. Okay, so that's your first step of UV-Vis. Setting it up, figuring out what the most absorbed wavelength is, and oftentimes we call it the wavelength max. And then from that, you can go and determine the same method. You would test this specific wavelength with standard solutions of different concentration at this wavelength, and that allows you to find a calibration curve, which you can read off once you've made it. Okay. The extra thing that not many people know about UV-Vis is you can also use it qualitatively to identify specific bonds. So if you have your wavelength max, or you have specific points of high absorbance at any of these wavelengths, this is in your data sheet, by the way, it would be suggestive that you have those bonds. So you can use UV-Vis spec to also do qualitative analysis. They've hardly ever tested this, so I wouldn't focus on it, but just be aware that UV-Vis is both qualitative and quantitative. I would not worry about these. This is a good question, though. If you have A and B, if you wanted to analyze the absorbance of solution B, what wavelength do you choose? Type in the chat. Analyze the absorbance of solution B. Seven hundred. I think we're in agreement. So you want to take the highest wavelength possible for B, the wavelength max, and that correlates at just about 700, probably a little bit below, probably 690, if I was to be exact, but 700 I'll give the leeway. Okay. AAS, finally, probably the weirdest out of them. This is the one that makes use of both an emission and absorption spectra and ends up canceling itself out. The main difference, you're using not a deuterium or tungsten lamp, you're using a hollow cathode lamp. The hollow cathode lamp contains the metal that you're analyzing, and it is exclusive to metals. AAS only can analyze metals. What happens in the lamp is this metal is excited, the electrons get pushed up to higher energy levels, and they all fall back down, which emits specific wavelengths of light. Those specific wavelengths will go into a atomizer, which is having that specific metal pumped into it to be sprayed into a flame. Those metal ions in solution will therefore be turned into atoms when the solution of water is evaporated. And so we say the sample is atomized, or it is vaporized even. And that means that there will now be metal ions floating, or not floating so much. There'll be metal atoms rather. I'll just put them as M's. M, all throughout that flame. So when the light goes through from the hollowed cathode lamp, those specific wavelengths, I've drawn them as blue, green, and purple here. It probably wouldn't be this many colors, but those three wavelengths going through are all absorbed exactly by that metal, because it's the exact wavelengths that represent the intervals between energy levels in that metal. That's why it's important the hollow cathode lamp has to contain the metal that you're analyzing. And so when it passes through, you'll have absorbance of the light blue, you'll have absorbance of the green, and absorbance of the purple. That sample, you then select one of those wavelengths. So say you select purple, the monochromator will select only the purple light, and you analyze that specific wavelength for its absorbance. Okay. When you analyze this absorbance, can we use Beer-Lambert law for AAS? Yes or no? Can we use Beer-Lambert law? Can we use Beer-Lambert? And can we use a calibration curve? Which one can we use? We can use a calibration curve. Why can we not use Beer-Lambert law? It's a trivial reason. Think about the equation A equals epsilon times concentration times lambda. Not lambda, times length. Great. No cuvette. If you have no cuvette, because we just have a flame, it means we cannot measure length. So that means we cannot use Beer-Lambert law. This would be invalid for AAS. So the only thing you can use to analyze AAS is a calibration curve. Be very wary of that. Okay. And the only other difference is that the monochromator tends to come after the flame in AAS instead of before it. But the main differences are the cathode lamp, and you cannot use Beer-Lambert law. Here's a quick summary table of each of those techniques: AAS, colorimetry, UV-Vis. I would say if you have this in your arsenal, you can describe all of them and differentiate them all very well. So I would focus on using this as an overview and build your understanding around this table. Okay, let's move on to organic stuff. How are we going for time? We're a bit pressed. Okay, organic substances. How do we analyze those? So we have reactivity tests. We should be able to separate carbon-carbon double bonds. Bromine test. When does the bromine test, what should we say? When does it decolorize? In what situations? When will your bromine test decolorize? Nice. So it'll decolorize if you have a double bond or even triple bond. So to add to your response, Ella, I would say double bond or triple bond, or you could just say unsaturated compounds. And also it will still decolorize a carbon-to-carbon single bond if you have UV light. So you have to make sure you do your bromine test in a dark room. Cool. Hydroxyl groups, there's a fair few tests. Number one, sodium test. Sodium test is going to essentially react and produce hydrogen gas with any alcohol, primary, secondary, or tertiary. It cannot differentiate between the three. And the reaction is as follows. limitations you should be wary of is that if you react sodium with water, you're going to get a false positive. So when you do your sodium test, it's best practice that you actually add a dehydrating agent like calcium chloride that will remove the water from your alcohol and allow for a accurate test. Also, you get false positives if you put sodium into a carboxylic acid. So if you are any bit suspicious of a carboxylic acid when you're doing a sodium test, you should add an indicator first to test the pH. And if you find a acidic substance, you may get a false positive. Esterification test is pretty poor, but basically, if you combine an alcohol and a carb acid, concentrated sulfuric acid under reflux, you're going to get an ester, which can smell. I don't like this test, so I'm just going to cross it out. I wouldn't use that. I would use this, though. I would use the oxidation test, separates your primary and secondary from your tertiary alcohol. Primary and secondary are going to decolorize because they oxidize, and hence the oxidizing agent will be reduced. So the oxidizing agent gains electrons, going back to year 11, your oil rig, reduction is gain. The oxidizing agent becomes reduced and hence changes color from orange to green. And that's why you see this change in color from yellow to green, or in the case of manganate, from purple to colorless. Can you separate a primary and secondary alcohol using the oxidation test? It's like sort of, I would say, but you want to add a second test on top of it. So how would you separate primary and secondary alcohol if you're going to use a oxidizing agent? How do you separate primary and secondary? You could use Lucas reagent. This is true. That would be a separate test. Definitely valid. The more common one that you'll use right after an oxidation test is, because you made a ketone and you've made a carb acid, if you've done it to excess, you can just do a, for example, carbonate reaction. You can add in carbonate and see if one produces carbon dioxide. Or yeah, Josh, you can do a Tollens reagent as well, test for the ketone. But those would be the other ways you can separate the primary and secondary once you've done the oxidation. Okay. Lucas reagent. Lucas reagent is your best test for separating primary, secondary, and tertiary alcohols. It does it in one sweep. So you add Lucas reagent to your alcohol, which is zinc chloride with hydrochloric acid. That's your Lucas reagent. When you add it in to your alcohol, you will get 3 cases. Your primary alcohol will not react. So NVR, no visible reaction. Your secondary alcohol takes 5 to 60 minutes to react and turns cloudy, and your tertiary will be immediate. And it turns cloudy, forming this sort of oily layer on the top, which is actually a alk oxide. It is a alkyl chloride. Alk oxide is for the sodium test. Okay, so Lucas reagent, probably your go-to if you're separating primary, secondary, tertiary. It's just the easiest. Finally, you have tests for carb acids. You can do a pH test to show that they have a pH less than 7. You can either use litmus, so it turns litmus blue, or you can use a universal indicator, pH probe, whatever you prefer. Or to identify it, you can add metal carbonate, as I said before. So a carb acid reacts with metal carbonate, and it's going to form salt, water, and CO2. And you test for that CO2 using what test? Junior science coming through. How can you test for CO2? Yeah, lime water. I wouldn't say flame test. Flame test is for metals exclusively, so be careful there. Lime water, if you bubble the CO2 through lime water, it turns lime water milky. Cool. So a question like this, you should be able to separate. If you had A, B, C, and D, as well as E, separating out these one by one, I would first do bromine water to this double bond here. This would decolorize bromine water so you can separate A. You then have a carboxylic acid on the end. So you can do like a pH test, or you can do a carbonate reaction to separate out E. And then BCD, you can either do a Lucas reagent to separate primary, secondary, tertiary. So this being primary, secondary, tertiary, I'll do a Lucas reagent, or you can do an oxidizing agent, which separates primary, secondary, and tertiary. And then the primary and secondary you can separate using a, for example, metal carbonate once again, which will separate your primary, which gives off gas, CO2 gas, and then your secondary, no visible reaction. Cool. Okay, on to the big stuff. IR spec, mass spec, proton, carbon, NMR, lots to talk about here. So let's get moving. Infrared spectroscopy. The main ideas remain the same. As I said, it's all about absorbance of light, and how much you absorb is basically your infrared spec. What you need to understand is the specific type of radiation that is taken in by these covalent bonds in a covalent molecule, so an organic substance. Every single bond in a covalent molecule vibrates in its own way. So they can either be, as shown here, they can be symmetrically stretching up and down like this, or they can be asymmetrically stretching, or they can be scissoring, or they can be rocking side to side, wagging, twisting. There's lots of different ways they can vibrate. And every single vibrational mode has a different amount of energy. So let's just say we don't actually need to know what the numbers are for what the energy are, but symmetric stretching, I believe, has a lower energy state. And in order to go from symmetric stretching to a different mode, such as, let's say, it goes to wagging back and forth, that would require you to input the exact amount of energy in order for the symmetric stretching to swap to wagging. And that specific wavelength being absorbed can be, once again, measured. So the more that you absorb, basically saying the more of that specific bond you have. The more that you absorb, the more of that bond you have. And this relates to why our infrared spectra, the y-axis is transmittance, because it is simply telling you how much of that specific, it's wave number, but wave number is another way of saying wavelength. So I'll just call it a wavelength. It's how much of that specific wavelength is being absorbed by this molecule. And you can see in this case, there's a lot of this particular wavelength, or this wave number. So wave number 3350 per centimeter corresponds to some wave length. Wave number just refers to the number of waves per centimeter. And again, as I said, different way of saying wave length. Okay. Does that make sense for everyone? It's infrared radiation, I should say as well, that IR spec absorbs, hence infrared spectroscopy. Infrared radiation is a specific amount of energy that will hit a bond and change its vibrational mode to a new one. Different wavelengths through that spectra allow you to detect how much of a specific bond you have, because each bond will absorb different amounts or different quanta of IR radiation. Okay, so how do we actually do an infrared spec? It is actually important to understand how you do these methods and how they're different. I have heard this exam period, there's a fair few schools actually testing how you do these methods. So I don't know if there's any sign to go by, but I would definitely invest some time into understanding actually how these work so you can describe them in your own words. When you're taking an infrared spec, you measure how much light is passing through the sample at each wave number. So you're starting off with an infrared light source, which is split into two beams of equal intensity, similar to how we saw in UV-Vis. So you have a wavelength, it's split, reflected, and you have two beams of equal intensity passing through a reference sample. Let's call this ref. This is the actual sample, and they are detected ultimately at the end. So you have I naught being how much light passed through the reference, and IT being how much light was absorbed after passing through your organic sample. What you're finding is transmittance. Transmittance, is it I naught on IT, or is it IT on I naught? Which one's transmittance? Top or bottom? Only one of them makes sense. Top or bottom? Bottom, bottom, good, bottom. So because IT is less than I naught, has to be on top. Otherwise, you end up with a transmittance which is higher than what you started with. Doesn't make sense. So this is your transmittance formula, and this is what you're plotting on the y-axis. How much of the light was absorbed, and I should show this with a dotted line too. This would end up being a lower intensity after passing through the sample. Cool. And essentially, you're scanning across the whole infrared spectra and plotting the transmittance at every single wave number. And hence you get this continuous looking line, which goes from high wave number meaning short wavelength, and short wave number meaning longer wavelength. So you're scanning from short wavelength to long wavelength, all the way across. And you're seeing which specific wavelengths are absorbed a lot. And we refer to these then as our troughs, as you've hopefully come across by now. And the troughs are what we care about. The troughs tell you specifically what bonds you have. And you can find all of that data in your data sheet. So depending on where that trough lies and its wave number, you can determine using each of these ranges what you have, but also using the breadth of each trough, you can find out what some of the more closely packed troughs actually are. So alcohols and acids are stated as broad and very broad. Alcohols having this smooth looking appearance, whereas acids have a more bearded appearance and being even broader. Amines I want to be careful of. They typically have a twin trough appearance, and they actually lie in the same region as alcohol, so they can be very confusing. I'd always be super careful if you get something that looks like it's an alcohol but doesn't quite have that smooth appearance. I'd be wary it could be an amine. And this shouldn't say alcohol here. Okay. When you describe a trough in your exam, there are three things you describe, probably two that are essential, one for extra brownie points. The wave number, essential. You have to say what the wave number of the trough is and be specific as possible. You cannot be penalized for being too accurate. You should be able to say the depth. This is probably the optional one. You describe it as either weak, medium, or strong, and that would be correlated to these sort of depths. And lastly, the breadth. Is it a broad trough? Is it a very broad trough in the case of an acid, or is it narrow? I wouldn't really use sharp as much, just keep it simple, very broad, broad, or narrow. And if you're not sure, you can just say moderately broad or moderately strong to kind of be on the fence, but try to be specific if you can. Usually it's quite unambiguous. Fingerprint region. Do we read any troughs in the fingerprint region? Controversial answer. Do we read any troughs? Okay. Ella's been paying attention to my classes. So no, except when you have a trough around 1,000 to 1,300. This is the case where you might have a C to O single bond. And that's not always the case. So whenever you see something in that range, a deep, narrow looking trough from 1 to 1003, you consider maybe I have an ester on my hands, or maybe I have an alcohol. And usually you can look at the higher part of the spectra, the higher wave numbers, and you can determine whether you have an alcohol or a carb acid, which has that C single bond O, or if it could be an ester. So I want you all to be very careful to never rule out an ester if you have something in that 1 to 1300 range. And you would write about that specific trough. That's the only one I would talk about in fingerprint region. Everything else is too complex. Don't worry about C, I think C to C single bond or something or rather in that range as well. That's not worth talking about. Okay. Broad troughs, separate them. As I said, alcohol smooth, doesn't overlap with the CH, which is around high 2000s. The acid is broad and beard-like. It does overlap with the CH. And for amine and amide, they appear above the CH and usually have this twin appearance. Just always be careful of those as well. You would usually use your other spectra to confirm these. So we'll go on to those. Okay. Mass spec. Very confusing for anyone who doesn't do physics. When I think about mass spec for chemistry, you want to keep it simple. You want to keep it very, very simple in physics terms. The first thing you want to understand is force equals mass times acceleration. This is your junior science bread and butter. Force equals mass times acceleration. What does that actually mean to us? And I'll put the arrows for the physics students here. What does that actually mean to us? If I have a really big mass and I apply the same force to it, will it move much? That's basically what we're trying to answer with this equation. And I'll give you the example of a pebble on the ground. Say you come along and you really hate the pebble and you kick it with your foot. When you kick that pebble, the pebble is going to accelerate off very quickly at a very high acceleration. And the reason is because acceleration is equal to force on mass. If your force is your foot kicking and the mass of the pebble is really small, the pebble is going to fly very fast. It's going to accelerate quickly. Counterexample, replace it with a boulder. If you kick the boulder is not going to move. Because the mass is so high, you have a massive mass on the bottom, and let's make it even bigger, massive mass, that when you kick it with the same force, the acceleration is so small that it barely moves. So that's your relationship between force, acceleration, and mass. And that's the crucial understanding for mass spec from a basic standpoint. Are there any questions on that? F equals ma. Okay, that's about to come into play again. 2 physics concepts you just need to accept if you don't do physics. Number 1, if you put a charged particle between a positive electric plate and a negative electric plate, the positively charged particle will be electrostatically attracted to the negative plate if it is positive. It will attract to the opposite charge. So opposites attract. And in mass spec, the only thing we use, the only ions we have are positive ions, as we should know. So here, the positive ion will be repelled from the positive plate and attracted towards the negative plate. And that is related by acceleration equals charge times electric field divided by mass. So all we need to know for electric fields, the charged particle in an electric field will be accelerated if it has a charge. Cool. And that gives our particle speed. That's the whole point. Our particle gains v, or velocity. It gains speed with a direction. Okay. Number 2. Charged particles' velocity in perpendicular magnetic field enter centripetal motion or circular motion. Bunch of physics. Don't think about it too much if you don't understand physics. All you need to understand is if I put my positively charged particle into a magnetic field. So here, these crosses mean the magnetic field actually goes into the page. All of these crosses, the magnetic field goes into the page. So when the particle goes into, actually, I'll put it this way. The particle goes into the magnetic field, it is going perpendicular to that field. That's what we mean by perpendicular to the field. So it's entering, and then it starts to bend. It experiences another perpendicular force, which you can understand with the right-hand rule. I'll keep it really simple. Velocity is your thumb. Index finger is a magnetic field. So the magnetic field is going into the page. And my thumb is the particle, which is going to the right. So then the force that it experiences is the rest of your fingers pointed upwards. This is the force that this proton will experience, an upward one. And I'm using my right hand for a positive particle. So the force is pushing it upwards. And as the particle starts to move upwards, you can see that that perpendicular force also starts to move, and your particle actually moves around a central axis and rotates like this. And that's your circular motion that we're talking about. This movement of the force being applied being perpendicular to both the field and the velocity means your particle will move around in a circle. Okay. Why does that matter? Because this circular motion allows us to separate all of our different masses. So if I draw two different trajectories, I draw this one here, where the particle bends more, and I draw this one here, where the particle bends less. Is A or B representing a particle that is heavier? A or B? A heavier particle. A or B? Got a good mix. Lots of A's, lots of B's. So think back to that case where you had the pebble, you're kicking the pebble flies very fast. It's accelerated very quickly. Pick a boulder, the boulder doesn't move. B is your heavier particle because it is going to be accelerated relatively less compared to A, which is a lighter particle. You can think of it as your pebble, a lighter particle, which will be accelerated relatively more and hence makes a more sharp deflection. So you're essentially separating all of your different masses based on how much they're accelerated by the magnetic field. And this is the mass spectrum that we talk about, this spectrum of all these different masses that are being accelerated by different amounts. And that allows us to form that whole crazy looking thing, this one. That was the background knowledge. Now let's actually explain how mass spec works. This is the setup. You have 4 phases in mass spec: ionization and fragmentation, acceleration, deflection, and detection. This setup, once you understand it, makes a lot more sense than just trying to rote learn. The first thing that happens is you inject your organic sample in. And I always like to explain this through an actual example. So I always take ethanol because it's easy to draw. H, ethanol. You put ethanol into your ionization chamber. So this setup here, this is your ionization chamber. Ionization chamber. When you put that sample into the ionization chamber, it is heated up to be vaporized, and then it is struck by a beam of high energy electrons. Electrons passing and striking it. And what can sometimes happen is those electrons can strike a bond. And in that bond, a covalent bond, you have 2 electrons. What can happen is the high energy electron can dislodge one of those electrons along with itself. So what gets left behind from that covalent bond is a single electron. We call this a lone radical electron. And this whole molecule, if it's lost an electron, what must its charge be? If it lost one electron, what must the charge of this molecule now be? Plus, 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 plus. Good. Quantify the plus, 1 plus, or just plus. And we refer to this ion as what? It is a cation, but it's a specific name. Specific name. Fragment. More specific, it is a sort of, no, I wouldn't say fragment. Fragment comes in a second. Good. Molecular ion. This is your molecular ion. Your M plus. That really high signal you see all the way on the right. It is essentially your molecule minus an electron after it's been struck by an electron beam. And therefore, it has the mass of your whole molecule. That's going to be important in a second. So you make your molecular ion. But on top of this, we're not done. We also make, as I think it's Esther in the chat, as Esther said, there's a possibility that this molecular ion that has one lone electron can also be struck by another electron. And if that single electron gets hit by another electron, it can also be dislodged. Or the single like weak-ish lone radical holding this molecule together can be cleaved. And you end up creating a separation where the left part of the molecule can end up cleaving off. And this would form a positive ion because it loses that electron. And the other side with this OH can be separated as well. And this one of the sides will actually maintain that electron. So say the OH maintain the electron. This OH would not have a charge. It would be a radical. The lone electron can go to either side, and so you can end up getting both of these fragments as ions. But the point is, every time you cleave them, only one of them will be an ion. And so this is a molecular fragment. And it also has a positive charge. So in this ionization chamber, you are making the molecular ion and fragments of that molecular ion, which also will have a +1 charge. And all of those will be pushed into a electric field. So why is it important? We touched on the electric field before. What does the electric field do to the positively charged particles? What does it do? Positively charged particles goes into an electric field. What's going to happen to them? Let's say you actually made this fragment as well, plus, and we said that this was M plus, this was X plus, and this was Z plus. You would essentially be pushing M plus, X plus, and Z plus in between a positive and negative plate. The positive plate repels the positive charge. And so all of these fragments get accelerated towards the negative plate and gain velocity. They gain speed. And they gain velocity before entering a magnetic field. So we have a magnetic field here. The magnetic field is perpendicular to this beam of positive ions. And you have that deflection that happens, separating out the lightest and the heaviest fragments. So here, X plus being OH with a molar mass of 17 grams per mole is the lightest. CH3, CH2 with a molar mass of 29 grams per mole is the second lightest. And finally, ethanol itself is going to have a 46 gram per mole molar mass being the heaviest. And you can see that the lightest is deflected most, the second lightest deflected a little bit less, and the heaviest deflected the least. And this is our idea of mass spectra, separating everything into a spectrum by mass. Are there any questions there? I've spoken a lot, and there's not very many questions. Either you've all got it completely, or we're holding back some questions. Okay, cool. I'll take it as we've got it. Let's keep going. So what do you need to actually look at in a mass spectra? You need to look at the molecular ion. What does a molecular ion tell you? So we know it's 72 here. What does molecular ion tell us? Molecular mass, good. If we see that the mass per charge is 72, this tells us the molecular mass is approximately 72 grams per mole. Why is 73 not the molecular ion? Because a lot of people say, oh, molecular ion is the highest mass per charge. Why is 73 not the molecular ion? Very common mistake. Doesn't have a peak. It has a very small one here. It does have a peak. A very small one. So why? Good, Zara. It's an isotope. And for bonus points, if you had said carbon-13 isotope, I would have given you an extra round of applause. So this carbon-13, this little tiny signal right above 72, is in about a 99:1 ratio with the 72 peak. And that represents the distribution of carbon-12 to carbon-13, 99:1. So you never want to confuse this tiny little peak that sits above your molecular ion with carbon-13. Be very careful of that. There's two other isotopes. What other isotopes are important to note that you can see around your molecular ion? Two very common isotopes. Bromine, good. Bromine 79 and chlorine 35 are the two you want to be careful of. They'll resemble a 1:1 ratio or a 3:1 ratio. And just be careful of those as well. The other important signals are your base peak, as well as all of these smaller fragments. So the base peak is the most common fragment. Usually it's one of the bigger pieces from the molecule. And each of these signals represents a fragment from the molecule. So for example, the base peak is representing, for pentane, it's representing this fragment here, the CH3, CH2, CH2. That is the base peak. What you need to be able to do is you need to be able to assign each of these signals, the main ones, to fragments within your molecule. And that's something that you should do if you want full marks in a mass spec response. I would say at a minimum, you identify at least one fragment. If you want to be sure, you identify every fragment in a big 8, 9, 10 marker. Okay. Common fragments, isotopes, molecular ion peak, base peak. Hopefully, they're all familiar terms now. Okay. NMR. So very scary from the first time you would have done it. And George's got a question. So to measure the molecular mass, do you always use the second highest peak value? Not necessarily. Sometimes they won't show the carbon-13 isotope. So for example, here in this question, you can see it like maybe very faintly something here. Let's see another one. This one here. So they haven't shown you any of the isotopes in a less detailed mass spectra. They might just show you this. And they haven't shown you any of the peaks surrounding. So my rule is I will take the highest mass per charge signal that does not resemble any particular ratio that we have to be careful of. So the ones you want to be careful of are 1:1, being bromine. You want to be careful of 3:1, being fluorine. And you want to be careful of 1:99, which is your carbon-13. So be careful of those. Otherwise, it's just the highest signal. These are the only cases where I would take the second highest, if you know there's a bromine, chlorine, or if it's the 99 to 1, carbon 13. Good question, though. Okay, NMR. NMR, you can think of every nucleus which has what we refer to as a non-zero spin. A non-zero spin, meaning that you have an odd number of protons or neutrons. These nuclei will generate a magnetic dipole. And you think of spin as a nucleus literally spinning around like a spinning top. So here in this case, we have a proton which is spinning around, and the magnetic field is generated from the proton spinning around. So this magnetic dipole going upwards is generated from the spin. In proton NMR 1H or carbon 13, these have non-zero spin, which is what allows us to do NMR on these two nuclei. We couldn't do NMR on, for example, 12 carbon, because 12 carbon has 6 neutrons, 6 protons. It has a 0 spin, so it wouldn't work. So that's why we can do 13 carbon and 1H, but not something like 12C. Fun fact, we use it in MRIs. Nuclear magnetic resonance, as the procedure we do, has a few important phases. So we understand firstly, these nuclei are spinning around and they have a magnetic sort of dipole. It's, first of all, we have to know there's two ways that these magnetic dipoles can be orientated. They can either be parallel or anti-parallel when you put a magnetic field through them. So the way I like to visualize it is you have, to begin with, a bunch of haphazard nuclei that aren't really organized in any way. They all point in different directions with their magnetic dipoles. But the moment that you put a magnetic field through them, they will all either snap into a parallel orientation pointing the same way as the magnetic field with their magnetic dipole, or they can be upside down, and we call that anti-parallel. So anti-parallel or parallel. And the parallel orientation has lower energy than the anti-parallel. And in order to go from parallel to anti-parallel, you have to give the exact amount of energy to transition from parallel to anti-parallel, higher energy. Hopefully, we're about to see where this is going to go. So most of your nuclei will be in the parallel orientation. We can consider it almost like a ground state. And some of them will be anti-parallel, but we're about to put through the exact amount of energy you need to flip them. And that wavelength is in the radio range, the radio waves. When you put a specific radio wave through and it strikes the nuclei which are parallel, it allows them to flip into anti-parallel, absorbing the energy, and we call that phenomena resonance. And when they fall back down, they release out that same energy, and that's your signals that you detect on your HNMR or CNMR. And that can be detected to give you the spectra that you see. Well, not so much spectra, but your HNMR and carbon NMR. Okay, so what do we actually care about on CNMR and HNMR? The number one thing that you always look at for both of them is regions. The regions, the number of carbon regions or the number of hydrogen regions. Then everything after that, you start with your chemical shift, which basically just means how far to the left is something. If something is left, it is shifted, or we can call it downshifted. Once you've done that, the chemical shift can tell you specific structure, specific bonding that is around that carbon or hydrogen region. You get data for your carbon environments, you do not for your hydrogen, but they can give you HNMR data to use as well. Okay. That's all you would do for carbon NMR. But for proton NMR, there's a few extra things. For proton NMR, you can also be asked to talk about splitting, which gives you very precise information about how many hydrogens are located where. And lastly, you can also be asked about integration or area under the curve, tell you how many hydrogens are in a specific region. So in any NMR analysis, I would go through these 4 steps. For carbon, it's only 2 steps. You go through regions, the number of regions you have, and the chemical shift. For HNMR, you go through regions, chemical shift, splitting, integration. It's systematic. If you have a system, you will not forget to do things, and you will get the marks. Okay. Carbon environments. Propan-1-ol has how many carbon environments? Type in the chat. How many carbon environments in propan-1-ol? 3, 3, 3. 3. We have 3. And in any molecule, the maximum number of carbon environments is the number of carbons that we have. Propan-2-ol, how many carbon environments? 2, 2, 2, 2, 2. Good, 2. Because we have symmetry. Can someone explain why this carbon environment on the left is the same as the carbon environment on the right? Why they're the same? And feel free to unmute. It's probably easier to speak it that way. Yes. I would add a little bit more to that, Josh. They are attached to 3 hydrogens and a carbon, but something can be attached to 3 hydrogens and a carbon and be in a different region. Because they have the same electronegativity, I'm not sure if that's exactly how I would justify it. I'm not sure if you heard otherwise, but probably not. Both connect to the same adjacent carbon and have the same effect of deshielding. Yep, pretty much. And yeah, you can sort of spot this from symmetry. But the way that I like to think about it, and I explain it, is you say that this carbon on the left is bonded to 3 hydrogens, as well as a CHOH and a CH3. A CHOH and a CH3. So it's got 3 hydrogens and a CH2, CHOH, CH3. The carbon on the right has 1, 2, 3 hydrogens and is bonded to a CHOH and CH3. You say that they're bonded to exactly the same atoms in exactly the same arrangement. That is the criteria for carbon environments to be equivalent. Have to be bonded to the same atoms in the same arrangement at every point. And you can often see that from axes of symmetry. It makes it very easy to see when you have equivalent carbon environments. Okay. And so why do we care about environments? What do the number of environments show up as on a spectra? Peaks. Good. Peaks or signals, the number of them. So if you have 3 environments, you'll see 3 signals as we see here. Cool. When you're interpreting a carbon NMR, once you've done that, you look at the chemical shift, and based on the number, so say it's 204.9 of this signal here, we would go to our data sheet, compare it against all of this carbon NMR data and see that it would fall within this 190 to 220 range. So that means we have an aldehyde or ketone, and we have this carbonyl from an aldehyde or ketone. Okay. And that correlates to this carbon environment here with a carbonyl on it. And you can correlate each other region with a specific carbon environment. I wouldn't actually have to look at my data sheet to figure out that these two are correlating to these specific carbon environments. What makes a signal go further to the left? What makes one of these signals go further to the left? Upfield, I would have thought it goes downfield if it's further to the left. That And yes, de-shielding and higher electronegativity, but I would be careful of how we exactly word it. I probably presume you meant that the carbon that is bonded to electronegative elements or more electronegative elements is going to have its electron density drawn away. So this carbon attached to an oxygen has its electron density drawn away, meaning the electrons aggregate around the oxygen, and this carbon is left de-shielded, having no electrons around it, or significantly less. And that means the carbon nuclei will then require more energy to be flipped from parallel to anti-parallel, bringing us back to this whole mechanism. And that will cause your shift to be further downshift or downfield if you have a larger difference in energy between parallel and anti-parallel due to de-shielding. And that's why it goes all the way to the left for CO. For this second signal, 41.9, you can see it's not as de-shielded, but it's still de-shielded more than carbon region A. What's the reason for that? Why is B more de-shielded than A? B more de-shielded than A. Why? Closer to the, not the OH, but the C11O. I presume that's what you meant. Good, because it's also affected by the electronegativity of the O. Great, just to a lesser extent. So you have some degree of pull on that carbon environment. It's slightly de-shielded, but nowhere near as much as this carbon, which is actually directly bonded to the oxygen. Okay. Finally, just to ground everything, TMS is tetramethylsilane. It is a silicon with four methyls around it, and it is considered as a highly shielded molecule. We compare all of our signals against it. So this TMS at 0 is just like a control. It's a reference, and everything's shift is compared against TMS. Okay. As you probably would have seen, this is in your data sheet. Make use of it. And we're on to proton NMR. Okay. Proton NMR, not entirely different to carbon NMR to begin with. Same idea with hydrogen environments. To keep it simple, hydrogens attached to the same atom are in the same environment. So this hydrogen is attached to the same carbon as this hydrogen. They are in the same environment. First rule. Second rule, hydrogens attached to carbons which are in the same carbon region are in equivalent hydrogen regions. So if you have this hydrogen here, which is attached to this carbon, and you have this hydrogen here, which is attached to this carbon. First of all, are these carbons the same environment? Yes or no? Are these carbons the same environment? Yes, they are. And so therefore, these two hydrogens are the same environment, and therefore, so are all of these hydrogens attached to the same carbons. That's the logic we can use for hydrogen environments. The only other important case is where you have hydrogens attached to oxygen or nitrogen. So this hydrogen here attached to oxygen is its own unique environment as well. And that'll have an important exception with the splitting later as well. Okay. So hydrogen environments, very similar what we've done before. The shift, same idea. Further left it is the more downfield and the more electronegative elements are around it. The new things for HNMR are splitting and splitting or multiplicity. They're synonymous, as well as integration. So we'll start with splitting. Splitting is caused by a phenomena called spin-spin coupling interactions. And it happens when you have hydrogen regions and closely clustered neighboring hydrogen atoms on adjacent carbons. Take that, if you do want an explanation, it's kind of a bit beyond what we need, but that's what I would write. the way that splitting works, it obeys a rule we refer to as the N+1 rule, where N is the number of hydrogens attached to neighboring carbon atoms. It's important to note, though, that hydrogens that are bonded to non-carbon atoms, like oxygen or nitrogen, don't participate in spin-spin coupling, and so they will never have splits. They will always just be singlets. So looking at this here, let's start with C. I think C is probably the easiest one to start with. CH3, hydrogen region C. Why does hydrogen region C have 3 splits and is a triplet? Why is that the case? Why is C, the hydrogens in C, forming a triplet? Neighbor is 2 hydrogens. Attach the hydrogen, carbon with 2 hydrogens, follow the N+ rule. Yeah, good. Gives 3. So essentially it's 2 + 1 because on the neighboring carbon, there are 2 hydrogens. And hence this triplet is going to be 2 + 1 or 3 splits. Hydrogen region B. Why does it have 4 splits? It's because the 2 neighboring carbons are all the neighbors. This carbon, I'll actually highlight them. This carbon here and this carbon here. Together, they have 0 and 3 hydrogens on them. So the neighboring carbons have 0 and 3. 3 + 1 is going to give 4 by the N+1 rule, and that's why we have a quartet, or 1, 2, 3, 4 signals here. And finally, for A, we can see that this hydrogen environment on its neighboring carbon, the neighboring carbon has 0 hydrogens on it. 0 + 1 gives 1, hence we have a singlet present on A. N+1 rule. Any questions there? Or any questions on anything I've said in the last 30 or so minutes? Okay, cool. And the final thing is integration or area under the curve. If you see a integration sort of squiggly curve looking thing, and you see a number next to it, these tell you the ratio between each of the signals. It tells you the ratio of how many hydrogens are in each region. The ratio of how many hydrogens are in each region. So for example, for the green region here, there's only 1 hydrogen. Or the red region here, there's 1, 2. And for the purple, there's 1, 2, 3. Hence, it's represented in a 1, 1 to 2 to 3 ratio. That's what our integration will represent. Okay. So what you should be able to do is you should be able to visually inspect a molecule and say how many signals there should be, what the chemical shift of each hydrogen region should be relative to each other. You can't know the numbers off by heart. And you should also be able to see what the splitting is around each hydrogen. And I would say that's what you're expected to do for a band 6 level of understanding, to be able to write at that level. Okay. So extended responses like this, a lot to do for 7 marks to 10 marks. The things that you must do are all here. So if you're struggling to get to that 4-mark range, there's probably things you're leaving on the table in these organic spectral analysis responses. I would give you these tips to make sure you maximize your marks. Number 1, do not be scared of figuring out the molecule before you start writing. If you can do that, your structure will be better. Number 2, if you spend some time structuring your response before you actually start writing, it'll be more cohesive. But if you're struggling to actually figure out the molecule, then don't worry, just start writing, and then you'll build on it as you go. Number 3, be specific with everything you describe. Write the exact numbers with units, write the exact ranges, write the exact chemical shift, justify with exact details. Your marker will always reward you for detail. Number 4, You want to describe absolutely everything. You want to leave nothing on the table for your marker to say, oh, you didn't say that. So when you have this system that I've sort of given you to go through each of these spectra and describe everything, you can not possibly lose a mark if you say everything in these spectral responses. That being said, you have to create time in your exam to do that. So these responses, these extended responses, my advice is you always leave them to last. And that way you know how much time you have to actually flesh out all this massive detail. And controversial take, what worked for me was writing more than you think you need. If you're pressed for time and you're still struggling from a content point of view, this advice doesn't apply to you. But if you're aiming for a band 6 or higher, you are always better writing more that is relevant than you think you need. Always have more detail than you think you need. If they give you 4 spectra, you use all the spectra and you describe everything in 4 spectra in order to get full marks. Do not be scared of the extra writing paper. And regardless of whether they ask you for it or not, you include a drawing of your molecule and ideally the name as well. Whether it's at the start of your response to flex that you already know or at the end, it doesn't matter. You just need a drawing. Okay. We won't go through a full extended response because I'm sure you have many of those, but that's, I guess, my golden nuggets of advice if you were to go for full marks. I'll be very brief on this final inquiry question. It's a lot of mod 5, but the main things that you need to focus on, as shown in the basically only inquiry question, you need to be able to discuss chemical synthesis and design. What are the implications? Discuss through yield and purity, availability of reagents, reaction conditions, industrial uses, and environmental and social and economic issues. The main questions I ask you here center around yield, purity, and also rate of reaction. And you need to be able to discuss how you optimize those 3 things through the manipulation of availability of reagents and reaction conditions. Availability of reagents, what does that actually mean? What does availability of reagents mean? Seems like a very trivial question, but it's important to have it out there. What actually is meant by availability of reagents? Yeah, I like Zara's the most probably. Whether a reagent is abundant, if you have lots of it, that'll make a reaction go faster and you'll be able to make more. So it's basically just how much reactant you have as a simple idea. And then the factors that feed into that, that allow you to ensure how much reactant you have would be, yes, the accessibility. How easy is it for you to get that reagent? Is it renewable or not? Because you might run out at some point. That'll ultimately mean you have no availability. So availability, how much you have. You're trying to drive as high of a reagent concentration and amount as possible because that will give you the highest yield, the highest rate of reaction because you have the most collisions per second. First point. Second point is your reaction conditions. And you're discussing here pressure, temperature, catalyst. That's it, pretty much. You should be able to look at a reaction process, most commonly the Haber process. They do it to death, so know the Haber process inside out. You should be able to discuss how pressure affects the yield and the rate of reaction, how temperature affects the yield and the rate of reaction, and how catalyst affects the yield and the rate of reaction. So the best way to do that is just through an example. Let's look at the Haber process. In this reaction, if we run a high pressure, how does that affect yield and rate of reaction? High pressure, how does it affect yield and rate of reaction? Okay, great. So I think everyone's on the money. We're going to have a increase in rate of reaction justified through collision theory. Means a higher pressure, or in other words, lower volume, means more frequent collisions per second, increased collision frequency, and hence you have a higher rate of reaction. You can also say a higher pressure is going to shift our equilibrium to the right because there are less gaseous moles on the right. The system will shift to resist the change and shift towards the side with less moles to reduce the pressure. So you have an increase in yield as well. So it makes sense then for this particular reaction, we want to run it at as high of a possible pressure because not only do we increase rate of reaction, we also increase yield. Hopefully that makes good sense. The only thing you want to be wary of is you don't want to say, I want to run at extremely high pressure. Number one, it can be dangerous to run systems at extremely high pressure. And number two, it's also extremely costly. It becomes sort of not worth it after a while, economically, to run at extremely high pressure. So you want to say, I want to run the system at a high pressure, being mindful that running at too high of a pressure could also become economically inefficient, something like that. What about if we ran this at a high temperature? How does that affect rate of reaction? And how does it affect yield? We run at a high temperature. Okay, good. I think we've all got it there too. So we decrease yield because this is exothermic. So we're going to have a shift backwards. And we also increase rate of reaction because, as we know, an increase in temperature increases both forward and reverse rate. So net overall, we have an increase in rate of reaction forward. Cool. So how high of a temperature do we want to run this at? What would you say qualitatively? How high of a temperature? Or in fact, how do you choose what temperature? Nice. A moderate temperature or moderately high, I would probably lean a bit more towards the high side. Moderately high temperature in order to have a significant enough, say moderately high, in order to have significant enough rate of reaction, but also not compromise yield. So, and that would be what we refer to as compromise conditions. Massive keyword. Use this in your response and you will get the marks. The markers look for these two words. Compromise condition simply means where you choose a temperature or pressure that is moderate, meaning that you compromise some of the rate, but you don't compromise the yield, for example. Compromise conditions, big keywords. Lastly, catalyst. Do we want to use a catalyst or not? It's a bit of a no-brainer. Absolutely, we do. If we can and we have one available, yes. How does it affect rate of reaction? How does it affect yield? Good. Well, careful, doesn't increase activation energy. It will decrease activation energy. Actually, careful on wording, I would say it provides an alternate pathway with lower activation energy. Technically, it doesn't decrease the activation energy of the reaction. And then I would say that it has no effect on yield. So yield unchanged. Yield unchanged. And I would also say that it increases rate of reaction by decreasing the activation energy and hence providing an alternate pathway with lower activation energy and hence increasing the number of particles over activation energy, and it increases the percent of particles over activation energy, increasing success rate. Be very clear when you talk about collision theory, you separate increasing success rate of collisions and increasing frequency of collisions. They're two separate things. And in a good response, someone will talk about specifically which is being affected. Okay. Catalyst, pressure, temperature, compromised conditions. Pretty much that's the whole thing. There's a few smaller points, things like recycling reagents, reacting the reactants in the right ratio. But for the most part, those are the main ideas. And for the last few dot points, it's all very trivial in my opinion. The compromised conditions, it's a mod 5 revision. So in industrial uses of chemical synthesis, you can use it in pharmaceuticals, cleaning products, fuels, and environmental and economic and social considerations. You can sort of intuit these if you don't have notes on them anyway, but here they are. Okay, so I'm a little bit over time, apologize, but that's all of Mod 8 in 2 hours, just a little bit over. Actually, no, a little bit under because we started at 9:05. Are there any questions on any of Mod 8? I'm happy to go back and answer anything quickly. Are you required to identify, I'll put the direct message chats comments in the chat just so everyone can see. Are you required to identify the spectra? We need to do this in our trials for a mark, but is this also the case in the HSC? Do you mean like look at a mass spec and say that's a mass spec? Is that what you mean? Yes, you definitely are. You should be able to look at mass spec and say that's mass spec, or look at IR spec and say that's IR spec, or look at proton or carbon NMR and say it's one of the two. I think proton and carbon NMR are the only ones that are harder to differentiate. So if you're looking at proton and carbon NMR, what are the key differences? So this is a proton NMR. How is this different to a carbon NMR? I'll say two important things. Splitting integration, sure. Splitting, definitely. Not so much integration, that's kind of like optional information they can give, but definitely splitting. And one other thing, the axis. What do you mean by axis, Josh? What the x-axis indicates. Yeah, more specific, HNMR has a much smaller scale of shift. It only goes to about like 10 on the high side of things. But a carbon NMR will go all the way to 220. So you can instantly tell them apart, and carbon NMR will only have sort of these single lines rather than splits. Yeah, good, Ella. Goes up to about 200, probably 220, because you have the aldehydes and ketones. Can I recap AAS very quickly? Yes, I can. AAS. AAS. All right, AAS. So to recap it very quickly, hollow cathode lamp, emission spectra with specific wavelengths exclusive to that metal. Metal solution, which goes through an atomizer and goes into a flame. The flame then contains metal ions that are the same as the ones that were in the hollow cathode lamp. So those three specific wavelengths that I've drawn here are going to be absorbed exactly by the metal sample, since the emission spectra will match the absorption spectra. So they kind of overlap. And that means those three specific wavelengths are absorbed by the metals in the flame. And that's the property that allows an AAS to function if you have more than one metal ion in solution, because you can selectively choose, oh, I want to analyze the copper, so I'm going to use a copper hollow cathode lamp. You could have iron, magnesium, all these different ions. If you only want to analyze copper, the emission spectra selects the copper, and that's the power of AAS. You then have a monochromator, which selects one of the three wavelengths in this case. Say it's select the purple one. The purple wavelength, you can then measure the absorbance. You would initially do it without the flame. I think I did mention this before, so this is probably important. You would initially do a reference without the flame in order to get how much the intensity would be without any absorbance, and you would pick usually the highest absorbance, and then you select that specific wavelength with the monochromator again, shine it now through the flame, and you would end up with a sort of lower intensity because some of it has been absorbed. This sort of magnitude was absorbed, and you can measure how much was absorbed in different concentrations in order to get a calibration curve. Any questions on that, Jacob? Hopefully that makes a bit more sense. Okay, great. Do you have access to the notes for today's session? Unfortunately not. These notes are just for Catalyst students. So if you do want to join the exam program starting next week, you'll get access to these set of notes, all of the Mod 5 to 7 notes, all of our question banks, as well as all the content going forward for the next 8 weeks. Sorry about that. The recording will go up though, so you can reference the recording. So if there's no more questions, you're all free to go. Not that you were restricted to stay here anyway. Enjoy the rest of your evening. Hopefully that helped you disperse some of your Mod 8 problems. If not, happy to answer any questions on things that still don't make sense. And for next term, if you're keen to join our exam session, starts next week. We go for 8 weeks right up until the HSC. And for me, this program, when I took it, I found this to be the most beneficial period for me, where I took my exam mark for my trial, which was all right. It was an 88 raw, ended up bumping it to a 98 raw in the HSC itself. So a program like this is very, very good for helping you hone in your exam responses, having someone reading your responses and giving you that feedback each week, in my opinion, is probably the best thing you can do to get value for your time. And your time is probably the most valuable asset you have in this critical 8-week block until your HSC. Okay, that's all. Thank you all for coming. Good evening, and I'll see you in the next one.